Welcome, Professor Agarwal, for your talk.
Thanks. So first of all, I should thank Professor Ashish Sen for having me here, and Professor Pallav Mahapatra for the kind introduction. And of course, I can't thank all of you here enough. I know it's a Sunday afternoon and it's the last day of the conference. And so thanks for being here. So I'm going to talk about some basic, very simple problems in fluid mechanics and heat transfer, mostly in heat transfer. And we will focus on some of the sort of non-intuitive or interesting things that we have seen. And that's why I have titled it as some peculiarities that we have seen in the flow. And we will sort of first look at experimental evidence from our group, some from the literature. And in this talk, we'll be mostly focusing on trying to understand why they happen, trying to understand the analysis and the physics of that. So that's the basic sort of things. So I will be talking mostly on two things. First, in the gases. When we have gas flow in the microchannels, we see that there are some interesting flow physics that happens there. And then even when you go to liquids, there are some other things that happen. And this is one of the central sort of non-dimensional parameters. So there are two parts of the talk. In the first part, I will be talking about gases. In the second part, I will be talking more about liquids. So when we look at gases, the Knudsen number becomes a very important parameter, especially when you go at the microscales. And just to refresh, Knudsen number is defined as the mean free path of the gas to the length scale, characteristic length scale through which the flow is happening. And using this Knudsen number, one can define or demarcate the flow into several different regimes. Knudsen number typically is, in all container problems, we don't bring in this Knudsen number because it's supposed to be very small and smaller than 10 to the power of minus 3. But once you start increasing the Knudsen number by either increasing the mean free path of the gas, which is by reducing the pressure, and basically molecules of the gas are now far apart, or you start reducing the length scale, which is when you go to the microscale flows, then you start getting into the slip flow regime. And of course, you can go further into the transition regime and the free molecular regime. So, and of course, one simple calculation for flow of air, for example, if I just take this, which has approximately mean free path of 70 nanometers, more closer to 67 nanometers. This is with nitrogen, not air per se. One would find that the Knudsen number is like 7 into 10 to the power of minus 3, which is just getting into the slip, and sort of somewhere here is what you see. So that means the slipping effects will become very important. And so in this talk, we will be looking at the peculiarities that the flow exhibits, especially the heat transfer that we exhibit. Now, one can ask, where do we see this? So especially when we look at gases. So there are a few examples that one can look at. This is, for example, a MEMS device where the damping from the air could be very important when you change the position of this. And we can also look at a very different example. For example, if you look at soil, and we know that we till the soil, and the simple reason is that the roots of the plant also need oxygen. And these small porous things that you create in the process of tilling sort of serves as conduits through which the air will diffuse in and reach the soils. And of course, then you can think of that. If I have to analyze this, this is essentially like we will have to bring in Knudsen number effect, and everything that we're talking about here will have to be brought in here. And of course, flow in lungs. And of course, if you can go to a different scale altogether, but at a lower pressure, where we said the mean free path of the gas can increase, and then this sort of effect can also become very, very important here. So we take advantage of the fact of this dynamic similarity in our case, of the fact that Knudsen number the effect can be brought in by two effects, either reducing the pressure or decreasing the length scales. And we have done experiments using both these approaches, and we take advantage of the dynamic similarity. Of course, at the large scales, you can measure far more things and far more conveniently. When we go to small scales, then the amount of quantities that you can measure becomes somewhat limited. Now, I will take a very simple flow in a channel sort of a situation. This is, and look at the heat transfer. When we look at the heat transfer of that, one can say, okay, this is a classical problem. People have solved it. The textbooks have it. The solution of that, we know the Nusselt number will be 4.36, 3.65, depending on what sort of a boundary condition you put it. But so what is new, what is different, and why is the difference? So here I'm going to first look at a few of these effects. That, and I mean, it's very interesting when we look at the entire energy equation. So in some sense, if you want to look at it in a different point of view, you can say that energy equation has so many terms, and a lot of times we land up throwing one or the other, or several of these terms, and doing an analysis on this. But this is one problem where we have to really bring in all those terms. We cannot really simplify the equation. And so you can see that here you would have axial conduction, you will have expansion work, you will have viscous stress, and property variation, and so on. In fact, I have slide on each of them, and maybe we can get into why these are coming to the picture, and then later on we'll see what is the implication of that on the results that we would have. So let us say that when we supply heat at the wall, we expect all the heat to get carried downstream by the flow. This is assuming that the flow is from left to right. But what you see when you go for, again, in a flow, at the small scales or ratified flows, what you can see is that there is a large amount of heat which is also getting diffused upstream. And in fact, first times when we were doing these experiments, we were very surprised, and we did not expect that at all. And we tried to do a lot of things, a lot of changes in our experimental setup to try to get rid of this effect, whereas we could not. And of course, later on you realize that there is for these flows, the Peclet number can become. So again, if you look at Incropera, for example, you say that axial conduction in the fluid, it becomes negligible if Peclet number is greater than 150. That's what the Incropera, for example, would say. Whereas in these cases, Peclet number, which is a product of Reynolds and Prandtl number, starts becoming small, and then this axial conduction starts becoming very, very important for you. And of course, the Reynolds number and this Peclet number is small because the Reynolds number is small, either because of the small length scale or because of the small density, if you're looking at ratified gas flows problems. So that means that the second derivative of temperature with respect to x, if I'm just looking at that term in the equation, cannot be neglected anymore. And so, of course, the implication of that is that the upstream wall and upstream conditions start becoming very important for you. Now, the other thing that these flows exhibit is that there is a large amount of pressure drop that you can have. And this again coming from our experiments in our lab. A few centimeters, a 2 centimeter, for example, channel can have pressure drop as large. Pressure ratio inlet to outlet could be 1:7. So it's like a huge amount of pressure drop that you would have in these microchannels. So there is a lot of expansion work that would happen. And of course, that has to be brought in somehow into your calculations or into an analysis. Of course, the other thing one looks at, who can think about, is viscous dissipation. And of course, initially, when microfluidics, people were always talking about that this is a very, very important effect, the effect of viscous dissipation, because one can say, okay, it's a small length scale, so the gradients will become very large. And of course, the gradients square is what one would get into the viscous dissipation terms, and that can become important. But here, so that, of course, and of course, that is quantified by the Brinkman number in these microscale communities. So this is another thing that will also sort of start playing a role. One can also say viscous stress work. Now, this is somewhat interesting because what happens in these cases is that because of as you keep on increasing your Knudsen number, we said that there is slipping. So the first thing which happens when you increase your Knudsen number is that the no-slip boundary condition at the surface gets violated. So that means the fluid will not acquire the surface velocity of the surface, but there will be a relative motion that you would have. There will be some amount of slipping that you will experience, that the fluid will experience at the surface. And there will be a corresponding temperature jump that you would have. The temperature of the wall will not be temperature of the fluid will not be the same as the temperature of the wall. So the implication of that is, if you look here, is that at the surface, a solid surface, there is of course a shear, but there is also a velocity that is available, so that means that there will be some work that will be done. And that has to be also accounted for in these calculations. So these are some of the interesting sort of effects that you start getting into, and you will see that the implication of these effects will be quite profound when we are, I mean, in the results that you see. Of course, you can also say that there will be a large amount of property variation, and this is going to be brought about because temperature differences are large, and if the temperature, there is a large amount of variation in the temperature, there would be a correspondingly large variation in the properties, thermal conductivity, and anything else, viscosity maybe, that you will have to, again, account for. This is not something specific or unique to the microscale. This is something anywhere where the temperature gradients are large, you will have to bother about it. Of course, the implication of that is profound in the sense that it may mean that any of the non-dimensional numbers that you have, Knudsen number, Reynolds number, Mach number, Brinkman number, whatever you are using to characterize the system, are now going to become, these are no longer constants, and we'll have to, again, worry about how to deal with it. So, this is just to sort of motivate why things are expected to be different. And this is just one slide to sort of say that, okay, what people have done in the literature. There are studies looking at these effects in the past, and there are, but you can see that people have put in some of these terms in there in the equation, but not all of them, not all the terms together, and not everything at the same time. And of course, especially the fact that there is upstream dependence that has not really be accounted for. So, of course, the first work was from Sparrow in '62, and lately, after the pickup of microfluidics, there has been a lot of subsequent work in the literature which is out there. So these are some observations that we have from the literature, but then there are some interesting experiments which happened in our group a long time back. And the idea was we start looking at using a very simple system where we have low pressure gas which is flowing inside, and then there is a water jacket which is outside. And essentially is a log mean temperature difference, LMTD method, that is being used here. So using this sort of a heat exchanger, one can figure out what is the amount of heat transfer coefficient that we are going to get inside. So you essentially measure the 4 temperatures. There is water which is coming in and going out. So you measure the flow rate of this, flow rate of nitrogen which is there in the system. So 2 flow rates and temperature of water in, water out, and nitrogen in, nitrogen out. So there are 4 temperatures and 2 flow rates that you measure, and using that and simple sort of, you can back out what is the heat transfer coefficient that you would have, assuming that you know what is the heat transfer coefficient of water in the annulus. So this is a very simple setup, and when we actually did these measurements with different Knudsen number, which is by varying the pressure of the gas in the system, we were actually very surprised by the Nusselt numbers that we were getting. Or we got, and we went ahead and actually repeated. So this was early measurements in 2009, which is when we did, and we came back and revisited this problem again with another student who was here, and in 2018, and we saw that there were no issues with our measurement. We have to start thinking of it in a different way, and with the second measurement, second time we also started looking at local temperature measurement by putting a lot of thermocouples on the center line of the tube, so that we can see how the temperature inside the tube is varying. And really the low Nusselt numbers that we are finding are actually true or not. So what we see, this is one of the observations, that we see that the temperature, so first of all, there is some amount of preheating that we always get in these sort of systems, and because of the axial conduction that I was talking about, and we will see more of that as we go along. And so the temperature, so you can see that this is a very small length. So we had designed our heat exchanger to be like a meter or a little bit more than a meter long. as per some calculations, initial estimates or whatever we thought it should be the heat transfer coefficient. But whereas what we see here is like the heat transfer, the temperature rises very quickly in the beginning. There is some amount of preheating which is there, and then the temperature becomes very constant. Okay, so this is something again so what we are saying now, before we start getting into this, these are part of the motivation that the problem is interesting from its own right because of all these effects that you can see. And there are also interesting experimental observations which are very difficult to explain unless and until you start to get into more details about exactly where the differences are coming from. So what we are going to look at are essentially three different cases. The first case is where we will look at the gaseous flow in the slip regime. So we will see that maybe the effect of Peclet number, the low Peclet number would become very important. But one can ask the question, why? Is the Peclet number effect only confined to the slip regime, or should we have something similar to that in the continuum regime as well? So that's why we, although this objective came after this, but we are going to present it with first the low Peclet number gaseous flow results in the continuum regime and then in the slip regime, and also some influence of the upstream boundary conditions on the heat transfer. So this is the first part where, the first sort of section into this part where we sort of see that this is how the problem has been set up. It was set up numerically, and we are solving it under as realistic conditions as we could. So we have essentially a heated wall, and there is an upstream wall which is there, and it's a low Peclet number situation. It's just coming out from the fact that this is what you need to solve for these cases. And of course, we have the compressible form of the equations being solved here, and with all the terms in the energy equation also accounted for. So now this is the first result which we can see. This is what is shown here is like a tube. This is Z is equal to 0 is where the heating is started. So on the right side there is heating, on the left side there is no heating of this. What is being plotted here is the heat flux. So you can see that there is, and of course the contours are for temperature. So what you can see is that there is a lot of heat flux which is going towards the backside, which is what we are also expecting because of the low Peclet number. So this is Peclet number 5, and this is Peclet number 1. That is what is considered. And what you can see is that there is a steep rise in temperature at the beginning of the tube. And of course, there is a strong Peclet number effect, which is also what you see here. So again, as we had seen in the experiments, there is a small region where a lot of heating is happening, and there is not much action which is going to happen after that. Now, if you just push this a little bit further and start looking at the Nusselt number in the developing region and as it gets fully developed. So what has been plotted here is Nusselt number as a function of the Grates number. And this is for the upstream region, the first figure, and the second figure is for the heating region. And so this is all corresponding to negative x's. So x is equal to 0 corresponds to where the heating is being applied. So that's why these are with negative numbers, and these are with positive Grates number. And what you see interestingly is that again there is a strong dependence of Nusselt number on the Peclet number. The other thing that you can see is the things where things become asymptote to the fully developed thing. That is a strong dependence on the Peclet number is what you would see here. And you can also say that there is some sort of some peculiar behavior which is also seen, which we can sort of zoom in further and see what is going on. So what you can see is that if you just take one case and you look at Nusselt number as a function of Grates number, what you see is, and again there are two different cases, one which is with constant properties and the other one which is with varying property. So what we were very surprised to see is that when you put the more realistic variation of properties with temperature, which is that means it's a varying property case, you see that there is a shallow minima, that is what you get. So you see that, of course, when initially the boundary layer thickness is very small, so there is the Nusselt number is very large, and as the boundary layer develops, the Nusselt number is expected to come down. But what is interesting is that there is a shallow minima, which is what you get before you start recovering and going to the asymptotic value. And of course, there is a small difference in asymptotic value as well. That's what you see here. And we seem to sort of, again, if you start to break it down, start to look at the various terms in the equation and start to see where the contribution is coming from, which is leading to this sort of a behavior, you see that there is a radial advection. So normally, one would not bother about this term too much in the equation. It's like v dt dr or v dt dy term. That's what we have. So this is a term which starts becoming very important and starts leading to this sort of a behavior. That's what you see here. So this is just one sort of example where things can become very interesting. Now, this was, I mean, as I said, we were looking at the continuum, and this is some results. Of course, there are a lot of detailed results, parametrics, etc., which has been done to show that these results are robust and to show exactly where things map out. I will not get into all those. Those are too boring in some sense to all those details. But it's more sort of key things that I'm trying to capture here. So now if you move from the continuum to the slip regime, now the slip regime, as I said, that there is the flow experiences a jump in temperature and there is a velocity slip. And normally one uses these very simple model, comes from Maxwell, and of course there is a counterpart of that in temperature, which one can use. Of course, there are other models. This is not the original model. This is probably one of the simplest and most widely used models that we have. And we started, before we started solving them, we started to sort of look at whether we are able to reproduce things well, and both the temperature rise, I mean, the solution for the energy equations, solution for the momentum equation are compared with measurements from our lab and from the literature. Shrikant's classical paper, work done in IIT Madras, if I'm not wrong. So yeah, so that's the sort of the things that it seems to work pretty well. The agreement seems to be very well. Now, very interestingly, if you start using this sort of a system and seeing how does things change for various type of boundary conditions, one can see how the fully developed or the asymptotic value of Nusselt number varies with Nusselt number. One interestingly sees that as the Nusselt number increases, that means that the gas is becoming more and more rarefied. You expect the ability of the gas to transfer heat from the surface to reduce. So that means you expect the Nusselt number to reduce. So, and this is what you also see in here. But what is interesting is that there is an peak local maxima that you get before it starts to reduce. Now, what could be the reason for this is there is an actual conduction which seems to assist the heat transfer, and there is a slip effect which is increasing the amount of the temperature jump or the velocity. So again, these would have, effects of this is what one can, if you were to analyze this, this is what we believe leads to this maxima in fully developed Nusselt number. And one can also see the effect of upstream wall, and one can now start varying the Nusselt number. And you can see that this is where 0 is, there is where the heat transfer, the heat is being added, and this is all the upstream region. You can see that before the fluid even enters the upstream region, there is a preheating which happens. And in fact, when the early experiments in 2009, when we were doing this, we actually put another heat exchanger before this just for the fun and to see what happens. And we were very surprised that in the first heat exchanger also, where there's no heating, the heat had actually penetrated, which is very similar to what we are getting here. And we were so disgusted that there's something wrong with our measurement. We threw off all that. We have no records of that left, unless so we have to reproduce it. But it's when we saw these results, we were trying to look back and see if we can actually have those experimental data with us. So it's very interesting to see that there is so much back penetration of heat, which actually happens. And as I said, there is at least qualitatively we had data which shows that this is actually what is happening. And now if you were to look at these flows a little bit closely, and you see how does the temperature vary in the entire section, what you see is that, as I had been saying, there is a very steep rise in temperature in the beginning, and then there is very little which happens in the major part of the tube, and then towards the end there is again which is again some sort of a drop in temperature. This is what you see. Now what we think, so one can of course divide the flow into three distinct regimes. One is it's a heat transfer dominated, which is the first part. The second part, where this is a constant heat flux or heat transfer and constant sort of a temperature, constant, let us say a constant heat transfer of sort of a section. And then there is an exit section that exists. Now what we think, what is happening here if you look at it, I mean of course what is happening here is that there is an expansion of the gas towards the end as it goes to the reservoir, and that leads to a drop in temperature. But what is happening in the middle is actually very interesting, and if you were to plot the Nusselt number, one gets the three-part distribution for Nusselt number as a function of x in this case. So of course there is a Nusselt number which reduces, and then it becomes sort of constant, and then it increases. But now when you look at what is a constant value, it seems to be slightly negative, which is very sort of counterintuitive. You are giving heat, and it seems to have, there should be a positive Nusselt number, but there's what you actually see. These are simulations. We see that there is a negative, this is actually based on DSMC calculation, I should have said that. And we seem to have a negative value of Nusselt number here. Now so if you were to investigate it closely, what you see is that the viscous shear work, that is what I had mentioned earlier, seems to be very important here. And so it's not that the bulk temperature of the gas has become less than the wall temperature, which is leading to a negative value of Nusselt number. What is only that the local heat transfer, local temperature gradient at the wall is what changes the sign, and primarily because of the viscous shear work that is there at the wall. And that leads to a change. So that means that the heat flux there, the flux there has reversed its sign, but the temperature, the bulk temperature difference has not changed its sign. And that's what leads to a negative value of Nusselt number. And of course, towards the end, there is an expansion which is happening, which leads to, again, the heat transfer, the drop in temperature and the heat transfer again picking up. So, so what I've tried to sort of talk about is that there is all these various things that we see in our equations, and this is a very nice model system where one can see all these things at play. Okay, so in the interest of time, so these are some interesting inferences one can look at. So now in the interest of time, let me go to the second part which I wanted to talk about. Now this is a part where I will now move away from gases, so there are no Knudsen number effect. We will go to liquids. And the problem statement, this is like starting off with trying to develop a device and then also trying to look at the robustness of the device and other things in there. So the simple question that we are asking is, can we have a device which maintains things at a constant temperature? So you know that trying to maintain anything at a constant temperature is very challenging. You need to typically go for a phase change material, and phase change material is not very easy to find to any temperature if I say give me a device which maintains temperature at 88 degrees or something at 38 degrees, 37 degrees is the body temperature. So how do you maintain that? So this is not an easy problem or a simple problem. But what we also realize is that when you supply heat, you are supplying heat to the walls, and the passage through which the fluid is happening is actually a small part of the entire thing, which means that the wall thickness is actually much larger than the fluid thickness. So that means that the conduction, there will be some conduction in the wall, which will also come into the picture. And that conduction of the wall is what can be utilized in our case. So this was a simple idea that when we supply heat to a channel, let us say a constant heat flux boundary condition is being applied, what you see on the inner side, which is what is the fluid is facing, is going to be very different. And that is because of the conduction of heat which is going to happen. So if the flow is from left to right, and it's a wall heated case, so the cold fluid is coming here and it's going out. So temperature of the fluid as well as temperature of the wall, both of them will increase. So that means that this is now the hotter part of the wall, and this is the cooler part. So there is going to be heat conducting, which is in the other direction. So that means that there is conduction of heat, which is opposite to the direction of the convection, which is to left to right. So these two opposing effects that you get, can you not try to optimize, can you not try to change the relative magnitude and get anything that you want? Now, how do I get that? Conduction is, of course, you can change the thickness, you can change the material. But what you can also do is, if you want to do the convection part, you can start changing the shape of the microchannel. This is now what I will get into. So this is a very simple shape of, like, let us say if I go to a diverging passage and see what happens in there. So this is a detailed experimental simulation work that we did. And what is interesting, so we had 25 micron size beads, thermocouples, being mounted on the outer wall of the microchannel. And we measured all these temperatures. And what we were interesting surprised to see, of course, this is a very constant temperature is what you get in these cases when you go for an optimal temperature, optimal conditions, which should become even more clear when you see these images through the of temperature contours being taken from the infrared camera, IR camera. So you can see that as you start moving towards your optimal conditions, initially you have, as expected, a linear increase in temperature, or pretty much a close to a linear increase in temperature. But once you start getting into the right optimal conditions, you start to get a very uniform temperature distribution. And again, the idea is from where I had explained to you, so changing the conduction and convection. And of course, one can further ask the question is this just an accident? Is just two effects just meeting and it's okay? It's just one point. And so we actually did a lot of these simulations looking at the effect of angle, because it's a diverging passage, there's an angle, so there is an effect of angle, there's effect of depth, length, thickness, thermal conductivity, mass flow rate ratio, and heat flux, etc. So there are a lot of these parameters, and one has to do a detailed parametrics. So from there, one can, of course, understand, first of all, what parameters are most strongly affecting this phenomena. And the second thing is that you can show that there is actually not a point, it's actually a very reasonably large parameter range that you get over which you can actually make something like this work. How much more time I have? Otherwise, if you want me to wrap up, or if you want me to.
Yeah, I think you
Okay, so I wanted to get into some shape variation also on that, but I think we will not have time. So let me, so what we were also trying to sort of look at is just to extend this idea further and see not just as a function of these parameters, are there other shapes that one can find, or is there something very peculiar about this diverging thing? So one can pose the question as they're saying that I have some width here and some width here, which I have to maintain constant, but in between I can do anything to the shape that I want. And I would like to then get any sort of a desired effect that I would like to get. So from that point of view, I started looking at this problem, and we looked at, let us say, a hourglass shape. This is what we call as an hourglass shape. We have a divergence first followed by a convergence first followed by a divergence, or you can have the other way around, a divergence first followed by a convergence. And one can again show that one can sort of see a lot of these things that I'm talking about in these shapes as well. One can also quantify and show that there are several advantages that one can get in these cases. So I think this is to the conclusions here. So I will say that So basically what we have tried to look at is, of course, in the first part, the effect of a lot of these parameters, advection, conduction, viscous dissipation, pressure work, etc. All these are very important when we look at gas flow in microchannels. And what we also saw is that there is a large effect of actual wall conduction in the solids that one can adopt. And of course, this is some of the things that I could not show, but there are maybe some modification in the standard non-dimensional numbers that is required in some of these cases. But let me just sort of stop here and maybe just do this one self-advertising and say that this is one book that we have on microscale flow and heat transfer. One can look at it, especially if you are interested in looking at the cases when the non-continuum effects come in the flows. And the high Knudsen number flows, essentially, when you go to those cases. So in the Knudsen number scale, you are moving from continuum to slip to transition. So when you go to the transition regime, especially, then what happens? So if you are interested in looking at the answer to that, this book has a documentation of that. So you would need something which is beyond the Navier-Stokes. So we try to look at the so-called the Bernard equations, the so-called the grad equations. So the derivation of these equations is covered here, as well as what are the limitations and what are the alternative approaches that people have looked at. And some of the work that we have done in this line is also documented here. So I think I will stop here, and thank you for this opportunity.
Thank you, Professor Agarwal, for this very wonderful talk. I think now we can have few questions. So.
Okay, so I had a question to your slide 19, and then you brought slide 27, and I want to change my question.
Okay.
And but we'll go to 19 also at one point. But it's a very principled question. So I saw you were presenting results with Nusselt number, but then sometimes just heat transfer rate, which I agree fully. But the Nusselt number, I'm wondering about that. I mean, in the Nusselt number, you've got heat conduction, you've got some heat transfer coefficient, but your properties are changing everywhere. And normally, like sort of the normal engineering Nusselt number takes T here and T there, and you get some different. You haven't got that here. So, I mean, does Nusselt number have any meaning here?
Yeah, so these are, simulations. So from the simulations, you have all the data. So when you go to experiments, I agree that measuring some of these things may not be very easy, and some of the things that you are talking about will become.
And then you brought 27 with the negative Nusselt number, and that just confirmed. But if you could stay right here, I mean, if I understand the left diagram correctly, you're going backwards from the heat source.
Yeah.
And if it doesn't matter what Peckley number we take, but in any case, your Nusselt number is rising the farther away you get from the heat source. Can you give me a good physical explanation
that's why this is a very confusing sort of a plot maybe. So you have to look at all these things carefully. So you are starting off with a small x here, and you're going. Yeah, and this is actually, you go from, this is negative, so this is actually reducing.
Okay, I could not see that from here.
Yeah, so that's right.
I'm almost in the first row, but I could not see that. Sorry.
So it's not counterintuitive, it's actually whatever, just a simple documentation of what you would expect to get.
I didn't see the negative part,
Wall temperature measurement simultaneously, because you showed the central line. Did you show the wall temperature? Because
yeah, so we have only centerline temperature measurements. Wall temperature, we have, we initially when we were doing these measurements, overall heat transfer coefficient, what we were finding is that the wall temperature is essentially not changing. Yeah, so we have never really measured the wall temperature. I'm not saying that, what I'm saying is it looks like very constant, but we have never really measured those. One can do it in the simulations. Simulations, we can see that how exactly the temperature is varying, and that I had shown. Yeah, so if you go here, for example, here you can see how the wall temperature is varying. So, but this is coming from the simulation, not from the measurements. Measurements, we have only the centerline temperature and the overall heat transfer coefficient, the heat transfer coefficient. Yeah, that's right. So that is why one has to really look at, that's where we have looked at each of these terms and seeing how, when we are close to the wall, when you are close to the center line, how the effect, how the relative magnitude of various terms of the energy equation, they changes, how the gradient changes. So we have done the detailed analysis of that. So I just tried to present only the key things here in this talk.
Amit, Just a quick question. In which dimensionless number do you have heat capacity embedded? For example, if you did this experiment with helium instead of nitrogen, which part of this experiment would capture that change?
So you are thinking about rho Cp term?
Yes.
Yeah.
Would rho Cp occur anywhere in any one of these dimensionless numbers, or would you anticipate the behavior to be the same for a given Knudsen number, Reynolds number, Peclet number,
Okay.
whether you use helium or nitrogen?
Okay, so
Sensible heat in the gas.
Sensible.
okay, so of course, see Peclet number would have some of this, right? Cp mu Cp by k. There is Peclet number which is there, would cover that. Now, of course, Peclet number is not a strong function of which gas you look at. So that's where I think we have to start looking at things differently in that sense when you look at microscale flows and the conventional scale flows. And this is, I think, the point that I'm trying to make here, that when you start looking at these flows, because of all these additional effects that start coming to the picture, the picture that you start looking at, it becomes different. And whether it will start becoming a function of the gas itself, that's a scary sort of a thing, because if you have to do that, you have to account for which gas I'm working with, and then I see that what is the corresponding Nusselt number or whatever I'm looking at, I'm interested in. So that is a scary sort of a thing. But see, if I just look at a very simple gas wall interaction, okay, and the models that I have talked about here, even the Maxwell's model, if you look at, now there are some empirical coefficients which are sitting there, which is going to relate how much slipping that you are going to get, and how does that relate to velocity gradient. So the velocity gradient, for example, so let me just go to that slide. Yeah, so if you look at this model, for example, these are empirical things. Now, if I look at how exactly this sigma v, tangential momentum accommodation coefficient, starts varying, now you can look at it as a function of the surface, you can look at it as a function of the property of the gas, you can look at it as a function of curvature, and so many other things, temperature, pressure, and so on. And you start looking at whether there is a dependence of this sigma itself, because you can see that this is going to be like a boundary condition is going to affect a lot of the flow properties. And similarly, one can look at sigma t and so on. So one does find that there is a small dependence on, for example, monatomic gas and a diatomic gas. Okay, but the literature, data in the literature is still very scarce, although a lot of groups have tried to measure that. It's very difficult to still pinpoint and say that this is how the variation is and things are varying. But yes, it does seem to indicate that there is, we have to look at the heat, the community has to look at it with more care and really say that, okay, the type of questions that you are asking, they are very much there. One is worried about if I put helium in there, this coefficient, I mean, from whatever analysis or from whatever data collection and other things we have done, a survey paper we have written, you can see monatomic gas and a diatomic gas, for example, will behave differently. Okay, so and whether the triatomic gas will behave differently from that is not clear. Okay, so helium and nitrogen, yes, I do expect a difference in the behavior. Now, with respect to surfaces also, whether it's a copper, whether it is glass, whether it is platinum, whatever it is. So there is also some amount of dependence in there. And of course, Satya has done some of those works. Yeah.
Now, Professor Srikanth, I think he used helium, right? And
no,
the copper
his
tube.
was nitrogen. He used nitrogen.
And the copper tubes.
Yes, and copper tubes.
Right, but traditionally in many of these RGD literature, people used the glass tubes and try to measure these accommodation coefficients and all that.
Yeah.
By looking at the pressure drop. So most of the data available is not necessarily from metal tubes, if you look at it. So did you try different materials or just tried only one material?
No, we have actually done just flow measurements with different gases. We had one point of time, we had used 4 gases, not just nitrogen, which is what I shown here, but oxygen, argon, as well as helium. These 4 gases we had used. And copper as well as stainless steel tubes we had used, even aluminum tubes that we had used at some point of time. Thing is that none of the time our data is, we cannot really say beyond uncertainty that things are all falling under this uncertainty band. It's very difficult to say that there is a clear effect that one has. So that's where the problem lies.
And also for very high Knudsen number experiments, did you find it difficult to measure temperature using these conventional thermocouples you used?
No, these are not very high temperatures.
High Knudsen numbers, like you said transitional Knudsen number values. You are
Yeah,
reaching some.
yeah. So here, interestingly, we are not really getting into very high Knudsen numbers. These are all like at the sort of border of continuum and the slip regimes. And this is one question we always worried about. In fact, we were ourselves worried about in the very beginning. We spent a lot of time in trying to make sure that our measurements are robust. And yeah, so that question we have answered. Yeah, there is no issues with these measurements from that point of view.
Thank you.
So if there are no other questions, we will thanks Professor Agarwal again.
Thanks.
Thank you for
Thanks
the
for that.
wonderful talk. So there is a small event for